Well, hello. My name is Ricardo Born. I'm a civil engineer and we work in BS Consulting, a company focused in geotechnical engineering. Just some brief words about this kind of analysis. We believe that soil structure interaction is a key point when dealing with high-rise structures, and it's still a field that is evolving to more refined results. From the geotechnical viewpoint, the results of settlements, total and differential, the distribution of loads and bending moments in the piles, the interaction between the raft and the soil, which is the piled raft hypothesis, the interaction between the piles, which is the group effect, are very important topics that are only able to be achieved with some accuracy when using a 3D numerical modeling. So, along with a platform that enables this modeling, the soil properties might be modeled with the use of soil constitutive models. And MIDAS GTS NX allows this analysis to be done with all those prerequisites. So, this case presents a soil structure interaction of a skyscraper in Brazil. The presentation is basically divided in 9 topics, starting with a small intro, going to some building details. Then we go to soil characterization that was done in the site. We head then to the pilot testing program, which was undertaken, and finally we go to the model. So we start with the structural model in Autodesk Revit, then we go to the structural model in MIDAS Gen, and finally to the geotechnical model and the full model in MIDAS GTS NX. And we go to some results and some brief conclusions that we have about this job. So the building, which is the focus of the presentation, is a 55-story, about 168 meters tall, designed in a later soil of low resistance. Because of the size of the building and the soil found at the site, soil structure interaction was necessary to evaluate the settlements and also to evaluate the behavior of the structure. The structural team, by this case, did not work with MIDAS Gen, and their platform did not export for Revit or for another, so it was impossible to directly import their model. So what we do is next was our team replicated the designed structure with the very same geometry, very same load cases used by the structural team. So this model was full created in Autodesk Revit. So with the Revit MIDAS Gen link, the model was then exported to MIDAS Gen, and after applying some conditions on Gen, the model was finally exported to MIDAS GTS NX, where the full model was analyzed. So as I said, the building comprises 55 stories, resulting something close to 168 meters tall, meaning then one of the top 25 tallest buildings in Brazil today. The whole structure is designed in reinforced concrete, which is the most common type of structure here in Brazil. Each story has an area of about 440 square meters. We have a total of 18 columns, which are actually structural walls because of its size, and a total estimated dead load of about 300 meganewtons. Some other building details now about the foundation. It is a pile raft foundation with 106 CFA piles. CFA piles are the continuous flat auger piles. So each one with 100 centimeters of diameter and 3 30 meters long. Well, the raft has an area of about 680 square meters, and we can check this in the image in our left, which is an aerial view, picture took from a drone. So by this phase, the pile was already done, and what they were doing was excavating to then execute the raft. Now we head to the soil characterization. So by this site we had 5 standard penetration tests going something close to 50 meters deep, and also 4 piezocom tests which reaching depths close to 43 meters. So this site is located in the southern Brazilian coast. So its profile compromises layers of sand and clay due to the characteristics of its sedimentary deposit. With the results of the piezocom test, we can see the excess of pore water pressure starting from a depth of close to 14 meters. And this gives us important information. And also we'd like to say that in this region, the use of cone penetration tests to estimate pile load capacity became something usual by last years, mostly due to the quality of the test compared to the standard penetration test. On the next slide, I'll show you some results of pile capacity prediction based on cone penetration test. So here we are heading to the pile load testing program. The static pile loads, just to define it, is composed by a real scale pile, which is tested by applying loads, and by the same time the settlements are recorded for each load step. And the figure in the right shows the test scheme, which is basically composed by the test pile and the test and the reaction piles. So a program of pile load testing was undertaken, which included 3 continuous flight auger piles tested to a maximum load of close to 9 meganewtons. The static load tests were undertaken prior to the foundation construction, which allowed a better understanding of the behavior of these piles. The results of the pile load test were compared to the values obtained by theoretical approaches using methods based on SPT and CPT, so standard penetration tests and cone penetration tests, as can be seen in the load settlement curve. So there's a difference between them, and the provision of the behavior of the pile based on the cone penetration test method shows values much closer for those measured by the load test, which this result is mostly explained because of the nature of the test, which is, let's say, much more technological than the standard penetration test. And inside MIDAS GTS NX, the results from the pile load test were used to define the properties of the pile, as will be shown later. So it's very important to have pile load tests when designing a building foundation, and especially tall buildings. So let me show you a little bit more about the pile loading testing program. These are some pictures of the test. So the figure shows the pile load scheme composed by, you can see that the hydraulic jack, which applies the load, and that reacts against the reaction frame. In this case, we had 4 reaction piles to resist the forces. Also, an important equipment is the load cell, which allows the loads to be read with more accuracy. The geotechnical designers, in the case ourselves, started with the design of the pile load test. So we defined the type of pile, the diameter, the length, the maximum testing loads, and also the reaction system. So we followed up the execution of the test, and later interpreting the results. Well, now heading to the structural model, it all started in Autodesk Revit. In this case, the structural team, as I said, did not work with MIDAS Gen, and their platform did not allow to export to Revit or to export to some kind of file that could be imported by MIDAS Gen. So our team replicated the design structure with the very same loads and load cases used by the structural team, and this model was full created in Autodesk Revit. All the materials, sections, properties, the analytical model, and loads were applied directly on Revit. I'll show you a bit of the Revit interface now. So this is Autodesk Revit 2017, and we have our full model of our building here. You can see we have all the geometry, and actually I think you can see the arrows, which are the applied load. And the thing is, we wanna take this model, which now is in Autodesk Revit. You wanna export it to MIDAS Gen. So the function, which is a link that needs to be installed in our computer. So if you go install it and you go to add-ins in Revit, then you go to external tools, we have this option to send model to MIDAS Gen. And it open, you just choose the name you are going to save it here. And here you can choose the element size, which is basically the size of the mesh that you are exporting. By this case, we have meshes in our slabs and also in our structural walls. So we can choose it. We have more finer or more coarser elements. Also, you can choose the unit and just click send, and it will save the MGT file. So let's head back to PowerPoint. So this is already the view of the model imported to MIDAS Gen, including all the geometric information, sections, materials, and properties. I'll show you a bit in the MIDAS Gen interface. So this is just a blank new file where we go to menu and we go to import MIDAS Gen MGT file, which was exported by Revit. Let's choose this one that I've saved before. Just take a little bit time to open up. As you can see, the message, it was imported with 0 error and 0 warning, which is good. Sometimes you may get some errors. So I'll just take a closer view for you to follow up. You can see the mesh. We could have chosen an option to get it finer, so the mesh should be finer. And we also show here in the menu what was imported. If you see, it already says here the number of stories. So we just need to configure to the information to talk in the same language, let's say with MIDAS Gen. We have the material, they were imported. So we have the material from the concrete that we have predefined there in Revit. You also have all the section, predefined section that was all defined in Revit. We have also this information about thickness, which is because of the slabs and the structural walls. We have some boundary conditions, some elastic links, and some bin and releases, which are also defined in Revit. And lastly, we have the loads. By this case, we have just applied the dead load case, but we also may apply others. And we left to apply live loads and wind loads directly on MIDAS Gen. So let's head back to PowerPoint. So inside MIDAS Gen, some conditions were applied as confirming the story information, some initial boundary conditions, and the wind loads that by this case the wind loads were derived from wind tunnel results, so were simply implied in MIDAS Gen. The model was then analyzed to check for inconsistencies, and comparing the reactions obtained by the structural team on their platform and those obtained by us on MIDASGen, the difference was smaller than 5%, which we've considered a very good approach. Along with the structural team, the behavior of the model were approved and then exported to MIDAS GTS to start the foundation iteration process. So let's head back to MIDAS Gen. I want to show how to export. So we have the full model here of the structure, and we want to export this to open in MIDAS GTS. So we go to menu, export, and we choose here MXT file for GTS. You just save it, and lately we can open in MIDAS GTS. Head back to the presentation. Well, going now to the geotechnical model, which is inside of MIDAS GTS NX. The soil mesh created is a square, 100 meters by each side, with 50 meters of depth. Layers were created based on the type of soil and resistance. For this case, we have created 7 different layers. For sands, the failure criteria used was the Moore Coulomb, in which the results of soil investigation may provide a good prevision of values of friction angle. And for clays, the constitutive model used was the modified CAM clay model. This model is a more complex one with some properties that are not defined very easily. So based on other soil investigation campaigns that we have in the local area that also have laboratory testing, we have knowledge of behavior of the clay from these deposits. So since there are some doubts about the behavior of clays, we have decided to make 2 different models using 2 different approaches. One from what we believe that the parameters really are, and another one from a more conservative perspective. So the results will show different situations. So what we expect is that the real result is being a point between these 2 approaches. So we need to understand that we have some soil investigation limitation. So we decided to work with this situation. So about the pile raft, we have 3.5 meters thick raft meshed as a solid element, and the material, which is concrete, was considered as purely elastic. Along with the raft, we have 106 piles, which were meshed as line to solid interface. Let me show you the model in MIDAS GTS NX. So let's check it out for first the model itself. We have all the soil layers, but let me show you first the raft and the piles. So all the 106 piles and the 3.5 meters thick raft. So let's go back to PowerPoint. For the pile model type, there are some some ways to work with piles in numerical models. And the best way would be to consider all piles as solids and define the interface properties and simulate its behavior. Well, the problem is that the model become way too heavy to compute. So a solution that also can be done in MIDAS GTS NX is to consider the pile as an element beam type, so converting a line to a beam and creating an interface to simulate its behavior. So besides it's not the best solution numerically speaking, it still offers good results when calibrated. So the model is equal to the soil, which is composed by a solid mesh, plus the piles, which are lines converted to beams, and interface lines to solid. So let me show you the piles actually are just lines that are converted to a beam, so they have a cross section, and also they have properties of a pile, so we can specify what is their behavior. So trying to obtain better values, we've done a pile load test calibration. So inside MIDAS GTS NX, we've created the finite element model to calibrate the load settlement behavior. So the geometry of the pile was reproduced, different load steps were defined, and the pile parameters were changed through trial and error, let's say, attempts. So that's it, what we call a class C prediction, where parameters are changed looking for convergence with measured values. The load settlement curve presented shows the pile load test results along with the finite element model created. The values obtained seems to fit well to what was measured. So this kind of model might be tricky because it might need many attempts, but we really believe that this is the way to go. You have better information, a better model if you go this way. So some numerical models of building foundations are made only by applying a load or pressure by the base of the columns. It is like retrieving the load values for each column from the structural team and applying it directly to the model. This might neglect the redistribution of loads in the superstructure and its stiffness or rigidity as you wish. So those results then might deviate from the real behavior of the structure, showing higher values of differential settlements. So looking to our model, we've tried to create a full model, which is the soil plus the pile raft plus the structure. And as was said, it is understood that differential settlements behavior seems to be closer than when using other kind of models. Another advantage is to be able to evaluate different load cases directly and also wind loads and other type of loads. So let me show you the complete model here. We have the pile raft. Now we have the building, the superstructure, and all the soil layers, all the 7 soil layers that we've created by this case. Now heading to the first results, we have selected here the results of settlements. The preliminary analysis tries to satisfy the maximum settlement criteria defined previously for the whole structure. And besides the absolute settlement values, an analysis of differential settlement is done, and also calculating the angular distortion, which tends to be more important. As stated before, as this model is working with the whole superstructure attached to the foundation, the results of settlements, and especially the differential settlements, tends to be more real due to the stiffness and rigidity of the superstructure. Let's take a look at the results in MIDAS GTS. Let's see only the piles. So in the results displacements, we can check the values of settlement in each pile. We can also select each pile node by its top and export these values of settlement. And here in the presentation we have called the settlement as delta. Here in the next slide I'm showing the results of pile loads and the distribution of load along the pile. So it's important to note that piles located in different spots along the raft tend to have different loads acting, and this can be evaluated through this analysis using the values of loads obtained to each pile and dividing by the settlement found for each pile, so we can calculate springs. Those springs are different for each pile, and this might be understood by us and by our colleagues, structural colleagues. The reason of this is mainly because of the position of the pile inside the raft, which can be affected by a location of a column. We may understand this as more or less loaded region, or due to pile group effects, which tend to decrease the performance of the pile, meaning that some may not offer the same reaction as others. So the generated springs for each pile may be sent to the structural team or simply exported back to MIDAS. The very same thing can be done for area springs. This is for the consideration of a pile raft hypothesis. So values of pressures above the raft might be divided by the settlement obtained in the same point. So this also might be sent to structural team or exported to MIDAS Gen. So taking a look in the results of axial forces in our piles, as the same I've said before about extracting those values, we can extract the value of each pile. So these values can be copied from MIDAS Gen and pasted to a spreadsheet in Microsoft Excel. So there we can calculate the spring and easily send to a structural colleague. Another set of results retrieved also from the GTS NX shows up the values obtained for bending moments in the piles. So these values are particularly important to define the structural design of these piles, as these piles are continual flight auger piles. The reinforcement cage length is very important to be defined, as there is difficulty to insert reinforcement when lengths are over 12 or 18 meters. So special procedures might be required, as special concrete and also vibrators attached to the cage. So these results might be particularly important when dealing with wind load cases, which this case may imply higher values in this situation. So let me show you the results of bending moment in the piles. we can check that the bedding moments in the piles in some side of the raft are much higher than from those by the piles in the middle. So these information are very good to be retrieved through a modeling like this. Well, for some conclusions, we consider that we had a successful interaction between Revit, MIDAS Gen, and MIDAS GTS NX. The key results from MIDAS GTS that we have analyzed are firstly the settlements of the pile raft foundation, which might be inside the range of the tolerable settlements for this kind of structure. For interaction with the structural team, springs can be created either for each pile and also as area springs, which are the contact of the raft with the soil. So this kind of information might be retrieved from the software, selecting the correct nodes and exporting the values of loads and settlements. So dividing load per settlement, we have a spring. So in the case of area spring, we might export the pressure and settlements and just divide pressure per settlement. Then we get an area spring. We have done this through Microsoft Excel, just copying the values from MIDAS GTS and pasting to Excel. Normally, an interaction between the geotechnical and structural teams are done by several iterations, starting with a set of loads sent by the structural, which results in a set of springs calculated by the geotechnical. Convergence between both models are then seek, and sometimes several iterations are needed for that. By the time full model is established using the same platform, the number of iterations needed to converge are reduced. So we really believe that this is a good way to go. So as a final thought, Professor Barata, which was an old foundation engineering expert in Brazil, he would say simply like this: we need to measure, and which means that for every effort that we are trying to do to evolve with complex models, we still need to measure the real behavior of the structure. And in this particular case, every column of this building will be monitored for vertical displacement since the construction of the very first story. This is to make sure that we are heading in the right way. Another thought is that we may have reached to an excellent numerical model, but it really relies on the information that we input in it. So having some quality soil investigation to retrieve reliable parameters from the soil is crucial. And also have a instrumented pile load test is crucial. So the results of our model all depends on the quality of this information. I'd like to make some acknowledgements to Mr. Luis Fernando Salles, to Mr. Renan Cordeiro, and to Mr. Marcos dos Santos, which are all part of our team and participated in this project. I'd like also to thank MIDAS for the invitation, especially Mr. Angel Martinez and Mr. Ray, and everyone for watching. Thank you very much.